We're going to have a look at the relationship between surface area and volume. The surface area of any solid is the sum of the areas of each side or face of that solid. So with a cube or a cuboid shape, there are 6 flat surfaces to consider. There's the two ends, and in our case that's W times H is the area. There's two sides, and in the case of this cuboid it's L times H. And there are the top and the bottom. In the case of this cuboid, that's W times L. So if you add all of those up, you get a total of W times H plus L times H plus W times L, all of that multiplied by 2, and that gives you the surface area of the cuboid. So working out the surface area of a cuboid shape is actually a little bit more involved than working out the volume. There's a little bit more arithmetic to do. Let's just do an example to make sure that we've understood that. Work out the surface area of this cuboid. This cuboid is 5 centimeters by 8 centimeters by 5 centimeters. So there are two ends, and those two ends are 5 times 5. There are two sides, and those two sides are 8 times 5. And there is the top and the bottom, and each of those is 8 times 5. All of that then has to be multiplied by 2. So we get 25 plus 40, which is 105, all times 2, which gives us a total of 210 centimeters squared. So we've seen that the volume of a cuboid is the length times the width times the height. So if we look at a straightforward cuboid shape, we've got a width, a length and a height. Now let's have a look at the area of that shaded area at the end, and this is called the cross-sectional area. Its area is the width times the height. So that's the area of the cross-sectional element of that cuboid. We can therefore say that the volume of the cuboid can be described as the cross-sectional area times the length. This is useful when we consider what happens with shapes called prisms. A cuboid is an example of a prism. The definition of a prism is a three-dimensional shape that has a constant cross-sectional area. So some examples are the cuboids we've been looking at, and these are shapes like, if you may play the game Jenga, where you build up the blocks in a tower and have to take bits out and not knock it over. Those shapes are cuboids, but they're also a rectangular prism, the same shape at each end and the same shape all the way through. They don't have to be rectangular in their cross-section. You can have prisms that are triangular in cross-section. Examples of this obviously are the box that a well-known type of chocolate confectionery comes in. You may also have seen triangular prisms in a physics lesson, for example, where a glass triangular prism is used to bend light and to show that white light is made up of light of many different colours. That's one use of a glass triangular prism. And you can have circular prisms. So the cross-section of a glass stirring rod in the chemistry lab, for example, they will tend to be circular all the way down, and therefore they are a prism. So in other words, if you were to take any one of these shapes and cut it anywhere along the shape and make sure the cut is parallel to the end, then you would end up with the same shape that you've cut out as the shape of any of the end points of that prism. And following on from what we've just looked at with cuboids, we can say that the volume of any prism is given by the cross-sectional area times its length. So we can work out the volume of a prism, whether it's a cuboid, a triangular prism or a circular prism, or any other kind of prism as long as we can work out the cross-sectional area. Okay, time for an example. We want to work out the volume and surface area of this prism. It's a triangular prism, and the triangle is a right angle triangle, and it is length 20 centimeters and its width 6 centimeters and height 4 centimeters. We've already said that the volume of a prism is the cross-sectional area times the length. The cross-section of this prism is a triangle. We know that the area of a triangle is half times the height times the width. In this case, we have a triangle that is 6 centimeters in width, and we have its height is 4 centimeters. So the area of this triangle is going to be a half times 4 times 6, and that equals 12 centimeters squared. So if the volume is the cross-sectional area times the length, in our case the volume is 12 times 20, and that is 240, and in this time remember it's centimeters cubed. So the total volume of this prism is 240 centimeters cubed. Now we're going to move on to the surface area. To work out the surface area, we've got to do this for each of the sides of the prism. We've got two ends, a long flat side, a back and a bottom part. We've already worked out the triangular ends. They're 12 centimeters squared each. That's the simple bit. We've already done that. Then, at the back, we've got a rectangle whose area is 4 times 20. So that's 80 centimeters squared. The base of the prism is quite simple as well. It's a rectangle with length 20 and width 6, so it's 120 centimeters squared. Finally, we get on to the large sloping side. In order to do this, we need to know the length of that sloping edge. Well, we know that that sloping edge is the hypotenuse of a right angled triangle, and we know two of the sides. So we're going to use Pythagoras to work this out. Simply, the length of that side squared is 4 squared plus 6 squared, so the length of that side is the square root of 52. Now we can work out the area of that sloping side. It's root 52 times 20 centimeters, that's 144 centimeters squared, and that's to the nearest centimeter squared. So we've got the area of the two ends, we've got the area of the back and the bottom, and we've got the area of the sloping side. The total area of the prism is now possible to be calculated. We have 2 times 12 plus 80 plus 120 plus 144 equals 368 centimeters squared. And remember, that's to the nearest centimetre squared because we've had to use a square root somewhere in our calculation. As you can see, none of the individual calculations themselves was too difficult. The hardest part was working out the length of the sloping side using Pythagoras. But you have to take care when working out these kind of surface areas because there are lots of individual parts. So the key, and I'm sure you know exactly what I'm going to say right now, is to write down everything you do as you do it, and don't forget to annotate the diagram as you go through and tick off the bits you've done. That way you are much less likely to make any errors, and you'll end up getting the question right more often than you ever get it wrong.